Swayam Prabha. Digital India. Educated India.
Now, we have discussed how to encode the number of hidden layers, the number of neurons to be present in each of the hidden layers, that is the topology or the architecture of the network, and how to encode the connecting weights, the coefficient of transfer function, the bias values inside that particular the GA string. So, ultimately the GA string is going to carry information, the complete information of the neural network. That means, it will carry the information related to topology, it will carry the information related to the connecting weights, then the information related to the bias value, the coefficient of transfer function. So, this particular GA string is going to carry the whole information of this particular the network, and we are going to take the help of the batch mode of training to optimize or to evolve this particular the network. Now, this shows actually one flow chart or the schematic view, like how does it work. Now, let me explain with the help of this particular flow chart the working principle of this genetic neural system. Now, as I told, the genetic algorithm is nothing but a population based approach. So, I have got a population size n, and this particular population of solutions are generated at random. Supposing that the first solution is something like this is a binary coded GA, the second solution is something like this, and the last solution is something like this. Now, if I concentrate on a particular the GA string, that is the first GA string, it will carry the full information or the whole information of this particular the network. Now, let us see how to implement the batch mode of training for this type of the network. So, I am just going to discuss the batch mode of training of this particular the network. Now, GA starts with a population of solution, and we create the initial population at random. We put generation is equals to 0. Now, here we have got a check the generation whether it is greater than equals to the maximum number of generations. Now, if it is yes, that is the end of the algorithm, and if it is no, so we concentrate on the first GA string. That means, we are going to concentrate on the first GA string, and we put GA string equals to 0, and here there is another check whether the GA string is greater than the population size. Now, if it is no, then we start with the training case, that is the first training case. Supposing that we have got some training scenarios, and the total number of training scenarios, let me consider I have got capital L number of training scenarios. Now, each particular training scenario carries information of the input and the output. Similarly, we have got capital L number of training scenarios. Now, corresponding to the first GA string, so we are going to concentrate on the training cases or the training scenarios. Now, here, so corresponding to the first GA string, my neural network is ready, and I am passing all the training scenarios one after another. For example, say here I have got a check where the training scenario or the case is greater than the maximum case, that is the maximum number of training scenario. Now, if it is no, then we calculate the output of the neural network. So, as I told that this particular neural network is indicated by, so this particular the GA string. So, we will be getting the output of this particular network and we use case equals to case plus 1. That means, I am just going to pass all the training scenarios one after another. The moment it satisfies so this particular condition, okay, so what we do is we calculate the fitness of the GA string. That means, after passing all the training scenarios, all capital L training scenarios, we try to consider the fitness, we try to calculate the fitness of these particular the GA string, and supposing that the fitness of the GA string is denoted by F1. And so, here we have got GA string equals to GA string plus 1. That means, we go for the second GA string. That means, we are going to concentrate on this particular the second GA string. And once again for this particular the second GA string. So, my network is ready. Once again we will pass all the training scenarios and we will be getting so this particular F2, and this particular process will go on and go on, and the moment it reaches this particular the criteria, that is GA string is greater than the population size, that means the fitness information for the whole population is ready for us. That means, we have got the fitness information, that is F1, F2 up to your Fn. And once you have got the fitness information for the whole population, now we are going to modify. So, this particular the population of solutions using the operators like reproduction, crossover and mutation. Now, the principle of reproduction, crossover and mutation, so those things actually I have discussed in some of the earlier lecture. Now, so this particular process will go on and go on, and this will complete actually one iteration or one generation of this particular GA, and GA through a large number of iteration we will try to find out some optimal design of these particular the networks. And as I told that there is a possibility that you will be getting multiple solutions, that means the multiple optimal neural networks, and you can use any one out of these multiple optimal neural networks for predicting the input output relationship. Now, this is the way actually the genetic neural system works. The working principle of this genetic algorithm, genetic neural system we have already discussed, and now actually what we are going to do, we are going to solve one numerical example just to make it more clear. Now, here I am just going to solve one numerical example, and we are going to solve this numerical example, and I am going to give the statement of this numerical example. A binary coded genetic algorithm is used to update the connecting weights coefficient of transfer function of a neural network as shown below. So, this is actually a very simple network having say 3 layers: input layer, hidden layer and output layer. So, on the input layer there are 2 neurons, on the hidden layer there are 3 neurons, and the output layer there is 1 neuron. So, this is nothing but actually a 2, 3, 1 fully connected the network, and let us see how to optimize. So, this particular your network with the help of a binary coded genetic algorithm. Now, the rest of the statement of the problem is as follows: the neurons of the input and hidden layer and output layers are assumed to have transfer function of the form y equals to x, that is the linear transfer function for the input layer, y equals to 1 divided by 1 plus e raised to the power minus a1 x, that is nothing but is your the log sigmoid transfer function for the hidden layer, and y equals to e raised to the power a 2 x minus e raised to the power minus a 2 x divided by e raised to the power a 2 x plus e raised to the power minus a 2 x. So, this is actually the tan sigmoid transfer function, and the connecting weights V and W we are going to vary in the range of 0 to 1. The bias value will vary in the range of 0.001 to 0.01, and the coefficient of transfer function, that is a 1, a 2 are going to vary in the range of 0.5 to say 2.0. Now, we are going to show one training scenario, and for this particular training scenario actually we will have to find out what should be the output, and that output we will have to compare with the target output just to find out the deviation in prediction. Now, the training scenario, as I told, is something like this, and the training scenario is nothing but the input output relationship. Now, there are capital L of training scenarios. The out of that, the first one is as follows: if I1 is 0.6 and I2 is 0.7, then output is 0.9. So, this is nothing but is your the input output relationship, known input output relationship. Now, if you concentrate on the GS string, the GS string will carry information of this particular network, that means your this 2, 3, 1 neural network, and it is having the fixed architecture, and we are going to use 1, 2, 3, 4, 5 bits to represent each of these particular the design variables. For example, 5 bits are used to represent V11, the next 5 bits are used to represent V12 and so on. So, this particular GS string is going to carry the full information or the whole information of a fixed architecture, that is 2, 3, 1 neural network. And as I told that our aim is to determine the deviation in prediction. So, for this particular the training scenario. Now, let us see how to find out. So, that particular the deviation in prediction. Now, to determine the deviation in prediction, so what you will have to do is, the first thing you will have to find out the corresponding to this particular GS string. So, you will have to find out the decoded value. For example, say if I just want to find out the decoded value corresponding to this particular the 5 bits which are used to represent the V11. So, this is nothing but 1 0 1 1 0. The place values are as follows: 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, and the decoded value is nothing but 1 multiplied by 2 raised to the power 4 plus 1 multiplied by 2 raised to the power 2 plus 1 multiplied by 2 raised to the power 1. Now, this is nothing but is your 16, this is nothing but is your 4, and this is 2. So, this is nothing but is your 22. So, the decoded value corresponding to these 5 bits used to represent V11 is nothing but is your 22. And once you have got the decoded value, now we can find out the linear mapping rule. We can use the linear mapping rule to find out the real value corresponding to that binary substring. Now, what we do is, now we have already discussed the decoded value of that, and we know the range. The range is nothing but 0.0 to 1.0. So, using the linear mapping rule, which I have already discussed, the linear mapping rule. So, we can find out the real value corresponding to this V11. So, V11 is nothing but V11 minimum, that is your 0.0 plus V11 maximum, that is your 1.0, minus V11 minimum, that is nothing but is your 0.0, divided by 2 raised to the power L. L is nothing but your number of bits used to represent, that is 2 raised to the power 5 minus 1 multiplied by the decoded value. Now, if I just write down this rule, that is V11 is nothing but V11 minimum plus your V11 maximum minus V11 minimum 2 raised to the power L minus 1 multiplied by the decoded value. So, this is nothing but the linear mapping rule. Now, here small l is nothing but is your 5, because we are using 5 bits to represent V11. So, very easily we can substitute all the numerical values and we can find out what should be the real value corresponding to your V11. Now, the same principle actually we can use to find out the decoded value and the real value for each of the variables. Now, for this particular V11, so I have already discussed like how to find out actually the real value. Now, you follow the same principle to find out the real values for each of these particular connecting weights V11, then 1213, V21, V22, V23, W11, W21 and W31, and we can find out their corresponding real values. So, we can find out their corresponding real values. Okay. Now, the range for your this particular A1, that is the coefficient of transfer function for your the log sigmoid transfer function. Now, here the range is 0.5 to 2.0, and once again by following the same principle you can find out what should be the real value. Similarly, corresponding to A2 I can find out the real value, for B I can find out the real value, and the range for B is nothing but 0.001 to 0.01. So, I can find out the real values for each of these particular the variables, and once you have got the real values, so my network is ready, and once this particular network is made ready, now I can pass actually the training scenario, that is the known input output relationship. For example, if I pass the set of inputs, I will be getting the output. Let us see how does it work. It is very simple. So, this I01, that is nothing but the output of the first neuron lying on the input layer is nothing but is your I1, that is the input of the first neuron lying on the input layer, plus B is the bias value, and if we just substitute the numerical values, so you will be getting this I01. Similarly, I will be getting I02, that is the output of the second neuron lying on the input layer is nothing but the input of the second neuron lying on the input layer plus bias value, and if you substitute the numerical values, so you will be getting this as I02. And once you have got this particular thing, so now actually very easily I can find out, so what should be the input of the hidden neurons. So, this your HI1, that is the input of the first neuron lying on the hidden layer, and I am also adding some bias value B. So, I will be getting, so this HI1 is nothing but I01 multiplied by V11 plus I02 multiplied by V21 plus the bias value is nothing but this. So, I will be getting this particular the input. Now, similarly, I can find out the input of the neuron, second neuron lying on the hidden layer plus bias value. I can also find out the input of the third neuron lying on the hidden layer plus bias value, and once you have got this particular the inputs of the hidden neurons, then using that the transfer function. So, very easily I can find out what should be the output. Now, so this H01 is nothing but the output of the first neuron lying on the hidden layer. Then comes your H02 is the output of the second neuron lying in the hidden layer, and that is coming to be equal to 0.791418. Similarly, this H03, that is the output of the third neuron lying on the hidden layer, and this is coming equal to be your 0.65 then 0.545. And once you have got your the output of your the hidden neurons, so very easily you can find out what should be the input of the neuron lying on the output layer. So, this OI1 is nothing but the input of the first neuron lying on the output layer, and we are adding the bias value, and this OI1 is nothing but HO1 multiplied by W11, HO2 multiplied by W21, HO3 multiplied by W31 plus B. And if you substitute the numerical values, so we will be getting the numerical values something like this, and this is nothing but the input of your the output layer. And on the output layer we have got some transfer function. So, using that, so very easily we can find out what is your OO1, that is nothing but the output of the first neuron lying on the output layer, and we can use this your the tan sigmoid transfer function, and you will be getting the calculated output is nothing but 0.981265. Now, this calculated output we will have to compare with the target output, and this target output is nothing but is your 0.9, and we can find out the deviation in prediction is nothing but 0.9 minus 0.981265. So, this is actually nothing but the deviation. So, the deviation is coming to be negative here. So, deviation is minus 0.081265. Now, this is what happens after passing actually the first training scenario. Similarly, we are going to pass the second training scenarios, third training scenarios, and all capital L training scenarios we are going to pass one after another. Now, this particular deviation, it could be either positive or negative, and that is why actually what we do is we try to consider the mod value of this particular your deviation, and the mod value of this deviation will be positive. So, for each of these particular the training scenarios or the training cases, we will be getting some deviation, and then we find out what should be the average deviation, and that particular average deviation will be the fitness of the GA. And as we discussed that for each of the GA string, if we can find out the fitness information, now we can use the operators like reproduction, crossover and mutation, and GA through a large number of iterations we will try to actually evolve. So, that particular network, so which can predict the input output relationship in a very accurate way. Now, if you see the reference like whatever we have discussed on genetic neural system, the same thing has been discussed in detail in the textbook of this particular course, Soft Computing Fundamentals and Applications, written by me. So, this is the reference for this genetic neural system. And now, to conclude or to summarize whatever we have discussed the principle of the genetic neural system, whose main purpose is to evolve a suitable neural network which can predict the input output relationship of a process very accurately. Now, the working principle we discussed in details, and after that we have solved one numerical example to make it more clear, and I hope that you have understood the working principle of genetic neural system, and by solving the numerical example, so this particular concept has become more clear. Thank you.